Okay, one of the things that I've talked about is how powerful organic chemistry is. If you understand the mechanisms of reactions, then you can do many reactions you've never done before and know what the products are going to be ahead of time because things go similarly or according to patterns. And so these three reactions, they sound all fancy, right? Hydrolysis of acid chlorides, alcoholysis of acid chlorides, aminolysis of acid chlorides. And not only is it generalizable that hydrolysis, alcoholysis, and aminolysis go by the same mechanism, so if you understand one of them, you can follow the other ones. And that's going to be the theme as I go through these three mechanisms, is that if you understand hydrolysis of an acid chloride, the product you get will be predictable. If you understand the mechanism, you can work out what the product's going to be. The other thing that's important here is you can have acid chlorides, acid bromides, or acid iodides will all react similarly. So again, if you understand an acid halide, it doesn't matter too much whether it's chloride, bromide, or iodide. It will react similarly, and you shouldn't be thrown off if in lecture we go over an acid chloride, but on an exam they use an acid bromide instead. So we're going to go through three general mechanisms using specific examples, and hopefully I'll be able to convey how if you understand hydrolysis, you will also understand alcoholysis. And that comes from a very simple idea that there's a functional group or a reactive site that's identical between a water and an alcohol. So if all of the reaction goes at the OH group of a water molecule, and the H that's attached to it just sort of sits around and gets carried through the reaction, then similarly, an alcohol has an OH group that can react very similarly to water, because it has the same components here, so the pKa of water is almost identical to the pKa of most alcohols. The reactivity of the OH bond is not necessarily going to depend a lot on what it's attached to, if what it's attached to is a simple carbon or hydrogen containing group. So as we go through hydrolysis, so hydrolysis would be reaction of water to split water and to get a reaction to go. Alcohol, and this is always hard for me to pronounce, alcoholysis is going to go very similarly. So let's knock out one mechanism, and as you learn this mechanism really well, it will totally help you to understand other mechanisms. So let's just add a typical acid chloride, and this would be called methanoyl chloride. So this is a one carbon group derived from the acid, methanoic acid, and methanoyl chloride would be the one carbon group, the carbonyl, methanoyl, with a chloride in place of what would be the OH group if this was methanoic acid. Now this carbonyl with the chloride on it is very reactive. The carbonyl is polar, so the positive end is generally going to be attacked by things that are negative. And then the chloride is a good leaving group. So this is set up for a substitution reaction. So this is substitution at a carbonyl. And in substitution reactions, we had a leaving group that leaves, and we have an incoming group. In this case, just like the substitutions we've seen before, SN1 and SN2, we're going to add in a nucleophile. So water is going to be our nucleophile here. And water is not particularly a great nucleophile, but the carbonyl is fairly reactive. And in the mechanism of this reaction, the lone pair of electrons on the nucleophile. It's going to go find the positively polarized carbon of a carbonyl, and it's going to go form a bond to that. And then in order for this carbon to maintain the octet role, we're going to have to push the pi bond off. So the pi bond from the carbonyl will become a lone pair of electrons on the oxygen. And this will form the famous tetrahedral intermediate, where the oxygen now will have 3 lone pairs and a formal negative charge. The water will be attached to the carbon of the carbonyl, and this will have a positive charge. The hydrogen is just going to sit there, and that's why this group can be modified and not really affect the reactivity, because it's just sort of along for the ride and it's just going to be copied over from step to step. And then the chlorine that's there is sort of getting ready to leave, because that's the way this guy will go. The methanoyl chloride will be attacked by the water nucleophile to make this tetrahedral intermediate. And then, so now we've introduced the new group that's going to be attached to the carbon. Now we're going to eliminate the good leaving group. So lone pair on the oxygen is going to reform the carbonyl, and the good chloride leaving group is going to leave, taking its electrons with it, again preserving the octet on the carbon. Now we're going to lose the chloride, right? And then the carbon reforms the carbonyl when the oxygen moves its lone pairs in there. And then now we have this OH plus from when the water came in and attached to the carbonyl. It's still there. And it doesn't really matter how the geometry is here. I think it might be less confusing if I go ahead and draw the incoming water in the same geometry that I had it before. But this again is just a 2-dimensional representation of a 3-dimensional thing, and there's rotation about single bonds. So what I just had and what I have now were really the same thing. They're just drawn differently, but this is similar to that. So a lot of times just copying accurately is a good way to go with this. And then the hydrogen I mentioned is just along for the ride the whole time. It's not really involved in the reaction. So then what we've done is we've replaced the chloride with the water. And now this guy, since we lost a negative thing, this is overall positive. And it's essentially a protonated acid. If acids are good at giving up its protons, protonated acids are really good. So our next step is the chloride is going to become a nucleophile. This protonated acid is the electrophile. And the lone pair on the nucleophile is going to deprotonate this compound, or this ion. And then this bonded pair is going to become a lone pair. So you'll see the 3 types of reactions we're going to go over. There's going to be the nucleophile attacks the carbonyl, forming the tetrahedral intermediate. The chloride leaves, reforming the carbonyl and going back to a trigonal planar intermediate. And then the chloride that's formed can deprotonate the protonated acid or whatever other intermediate is there. So it won't always be an acid. In this case, where we react water, we're going to get an acid. So we form methanoic acid, and the byproduct then is going to be HCl. Oftentimes they'll just put a minus HCl over the final arrow to say that the HCl is eliminated in the reaction, and then after we deprotonate the protonated acid, we just get the acid. So the overall summary here is acid chlorides, like methanoyl chloride, react with water to form acids, organic acids like methanoic acid, carboxylic acids, with the elimination of hydrochloric acid. So it's a good idea to learn the naming of acid chlorides, and then the three-step mechanism to turn acid chlorides into acids by reaction with water. And one of the things that we're going to do is go through, like I said, 3 types of reactions, and by changing the nature of the nucleophile just a little bit, we're going to get different products with different properties. Acid chlorides, acid bromides, and acid iodides are very reactive and very useful for forming a whole range of things, and it's just going to be modification of the incoming nucleophile that'll modify our products. So super exciting stuff for organic chemists who want to make a wide variety of molecules, and you don't have to memorize a whole lot if you understand things well. So go ahead and go over this a few times to make sure you understand the 3 steps in the mechanism: nucleophile attack on the carbonyl, elimination of the chloride leaving group, and then deprotonation of the second intermediate to form the final product.